This is Lab 5, Faraday's Law, Physics 2 by Alex Swatzka, Spring 2023. The purpose of this lab is to collect observational data of a magnet falling through a conductive tube of aluminum foil and then model this interaction computationally. Then to compare these two values of the computational predictions with the observed data that we gathered. The formulas that we are using in this lab are Faraday's law, the Biot-Savart law, the magnetic force on a loop, Newton's second and third laws, the time derivative of a magnetic flux of a dipole. Our results were that the experimental time took 1.24 seconds to fall through the aluminum tube, and the computational model calculated it at 1.183 seconds. The assumptions we make during this lab are that the magnetic and gravitational forces are the only ones present in the model, meaning that we are going to ignore air resistance, friction, or any other external force. And the system of this lab is the aluminum tube and the magnet. The initial results of this lab were that the aluminum tube had a length of 0.305 meters or 1 foot. It had a width of 0.006 meters, and a radius of 0.02 meters, a mass of 0.024 kilograms, and a mu value of 4.4. This value was gathered from Lab 3. An experimental value of t being 1.24, and then a computational value of time being 1.183. For the glow script model, we had to start by entering in the initial values, including the length, width, radius, mass, and magnetic dipole moment of the tube. Then we had to calculate the magnetic field of the bar magnet, then calculate the magnetic flux, then calculate the current in the ring, then compute the typical B field at each ring, then use those values to calculate the net force on the magnet. Then we had to update the velocity and position vectors in order to plot the time and velocity graph. As you can see here, at the results of the glow script model, we see the velocity and time plot, that they end up getting the total time in the tube being 1.183 seconds. And we see on the right here the model of the magnet going down through the aluminum tube. The results gathered from our glow script model of 1.183 seconds time and system is slightly lower than our observational data at 1.24 seconds. This is still very close, and the discrepancy in these can be explained by human error, and then also by outside forces that we assumed to ignore that actually affected our observational data. Now we ask these questions to investigate different scenarios of this model. First, we ask, what if the resistivity of the conductor were reduced as close as possible to zero, and how this would affect the dynamics of the falling magnet. Since the current is inversely related to the resistivity, as the resistivity goes towards zero, the current would increase significantly. This would result in the magnet taking longer to fall down the tube, since the upward magnetic force would increase, and the gravitational force would stay the same, seeing that the mass of the magnet stays constant. Then we ask, what if holes or slots were cut into the tube, and how this would affect the ring currents in our model. Holes that being cut into the tube would decrease the total surface area of the tube, which would result in the currents flowing through the rings to also decrease, seeing that the surface area and currents are directly related. This would result in the magnetic force to decrease, resulting in the time in the system to also decrease, meaning that the magnet would fall faster through our system.